Holy shit! We just picked up 60 horsepower with revised piping. I'm Gale Banks. Welcome back to Dyno Cell number 2. Last time we checked in, this stock Duramax L5P made 852 horsepower. In this episode, I intend to break 900 and use less fuel per horsepower doing it. To pull that off, we've made some changes to the exterior of the engine. First, we've improved the air intake system, laying down the two big-ass filters that used to be standing upright. We got rid of that 90-degree bend and moved the turbo up and out of the valley. Now the air is making a straight shot right into the compressor. To get the turbo up, we got rid of the aftermarket up pipes and fabricated our own 2 1/4 inch pipes with very gentle bends up into a 3-inch forged collector. In the process, we eliminated the stock turbo mounting foot. It's fine for the stock turbo, but we're doubling the horsepower, so the stock foot has become a major choke point. Coming out of the turbine, we replaced the short cone adapter to the 4-inch exhaust pipe with a long conical diffuser married to a 5-inch exhaust pipe. So now it's 5-inch to the exterior of the building, and then it increases to 10 up to the roof. We also replaced the worn-out rubber vibration damper with a viscous fluid damper so we don't break the crank. And we've also rigged it to measure crank twist. More on that in an upcoming video. So we did all this, the vibration damper, the air intake, the up pipes, the exhaust system, all to try to find power where most people don't look. Aaron, you ready to build some heat in this puppy? So we're wearing protection here in the dyno room. Later we're going to go rob a liquor store. I love the way my glasses are steaming up. This is really something new. We've set some warning flags on these 3 DataMonsters. The first one is compressor discharge temperature, and we've set that at 465 Fahrenheit. The second one is turbocharger shaft speed. We've set that at 130,000 RPM. And the last gauge here is turbine inlet temperature, EGT, and we've set it at 1650 Fahrenheit. All right, Aaron, you ready to bang this turkey? Let's go for it. Okay, folks, here we come. $98,000 turbine shaft, 250 mad, turbine inlet temperature coming up on 1200, 600, 700, go for it. Don't be gentle. Let's go, 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 go. 850, 60, 70, 80, 90, push it. Wait a minute, I just saw 912 horsepower. Holy shit. We just picked up 60 horsepower with revised piping. Oh my God. 912. Let's get into the data. I'm having a hell of a time putting my arms around this. We just made 912 horsepower with a stock L5P out of somebody's pickup truck. I mean, that thing is stock from the bottom of the oil pan to the top of the valve covers. We've never unscrewed a bolt on the outside of that thing except to upgrade the oil cooler, upgrade the vibration damper, upgrade the turbocharger, and upgrade the injectors. Oh, and we straightened out our big-ass filter arrangement, but nothing on the inside. We just pulled the data off this little tiny card. This is the guide we punch into the front of an iDash DataMonster, and it inhales up to 100 channels of data. There's so much new here. So much I've never talked to you about before. So let's just jump right in. Let's start with the cold air intake. There is no ram air on this setup. It's inducting the air in the room, which is the same temperature as the air in the shop. And it's pretty consistent day to day. Laying down the system and giving a straight shot through the two big ass filters and directly into the eye of the compressor gave us a little over 1/4 pound better pressure at the compressor inlet. And taking out the 90 reduced the work being done to the air flowing through the tube. And we picked up about 3.2 degrees Fahrenheit cooler air at the compressor. So what did that do for air density at the compressor? Since there's no ram air, it's kind of tough to have an increase in air density at the compressor. There's no vehicle speed here to provide ram air. So there's going to be a density loss. We went from 4.1 pounds per 1,000 cubic feet loss to 2.3. So we picked up 1.8 pounds per 1,000 cubic feet. What did that do for us? That gave us 5 more horsepower. We had a horsepower reduction due to density loss of 12.3 horsepower. Now it's reduced to 7.3 horsepower. You heard me right. We picked up 5 horsepower just by laying the damn thing over. Mind you, we're inducting almost 1,400 CFM out of that dyno room. Now we're going to move to exhaust system back pressure. Oh my God, everybody talks about back pressure, but nobody really gives you any facts about it. People don't usually associate a horsepower number with a back pressure number. But every pound of back pressure you can get rid of goes all the way back to the piston rising on the exhaust stroke. If you can reduce back pressure in the tailpipe, that goes all the way back to the cylinder, reducing pressure when that piston rises up the bore. And if you can reduce pressure there, you're going to liberate horsepower. Most of you don't read from right to left, but I'm going to ask you to do that here. We're going to go from the ass end of the vehicle all the way up to the exhaust manifolds on the engine. So starting with the tailpipe outlet, we have no back pressure. At 852 horsepower, the tailpipe contributed 2.3 pounds of the back pressure total. The turbine contributed 42 pounds of back pressure, and the uppipes and the turbine mounting foot contributed 7 pounds of back pressure. The total back pressure at the exhaust manifold outlet was 51.3 pounds. That 51.3 pounds acts directly on the head of the piston when it's coming up on the exhaust stroke. Just the static pressure against the head of the piston is 51.3 pounds times 12.9 square inches of piston crown. That's a cross-sectional area of the bore of the engine. So 51.3 per square inch times 12.9, we have 662 pounds of static exhaust pumping pressure acting on that piston. That's before it even moves. When the piston comes up the bore, the velocity is insanely high. That 662 gets multiplied quite a bit, and it varies with RPM. We're looking at it here at the horsepower peak RPM, and these runs, it's nominally 3,400 RPM. Remember that 662. Now, we made some mods. Our tailpipe went to 5-inch, but we put a conical diffuser coming off the turbine, starting with turbine diameter, then into the 5-inch, through the wall into 10-inch, up the wall outside. In both cases, on both of these runs, that 10-inch acts like a chimney in a fireplace. In other words, it's helping to scavenge the system. It's the same impact. We didn't change anything out there. So the back pressure we saw with the conical diffuser and the 5-inch pipe is much the same as the back pressure we see from a DPF with a 4-inch outlet, a short conical diffuser, a 5-inch pipe, and then our Banks ob-round exhaust tip. In other words, we saw 0 pounds of back pressure. Now you might say, is there something wrong with your sensor? Well, we used 2 sensors. We used a gauge pressure sensor and an absolute pressure sensor. And when the gauge pressure sensor said 0, the absolute pressure sensor read ambient air pressure. Basically, the tailpipe ain't there. But the turbine section, there's an increase of 5.4 pounds in the turbine contribution to back pressure. We're now at 47.4 pounds. As far as Eric's Y-pipe and that forged collector and the entire layout, those big radius 2 1/4 bends, the total contribution to back pressure dropped for the Y-pipe and call it the mounting foot from 7 psi to 0.2 of a psi. That's a winning design, I'll tell you. So the total back pressure now at 912 horsepower with additional air mass flow has dropped to 47.6 pounds. 47.6 times 12.9 gives me 614 pounds of exhaust pumping static pressure. That's a 7.3% reduction, and that removes parasitic horsepower used to push the piston up the bore on the exhaust stroke, and you now can get it out the flywheel into the crankshaft. We made a 6.5% gain in horsepower. What's going on here with this turbine drive pressure, if you will? This pressure differential across the turbine. So I'm going to take you to something you may or may not, a lot of guys talk about turbine drive pressure. Very few guys talk about turbocharger boost to back pressure ratio. This is a new iDash parameter, and it's probably a new reading for you, but it's one I've used all my turbocharging years. The old term, the old timer's term is crossover. It's the compressor outlet pressure divided by the turbine inlet pressure, but I take it one step further. It's the pressure differential from the inlet to the outlet of the compressor compared to the pressure differential from the inlet to the outlet of the turbine. I'm isolating the turbocharger. I'm not including a tailpipe. I'm not including an air intake system. Nothing. I'm just looking at the turbocharger. Is this the right machine for this engine? The turbocharger boost to back pressure ratio is the delta P, the pressure gain across the turbocharger compressor in PSI gauge, divided by the pressure requirement of the turbine, the delta P turbine, from its inlet to outlet in PSI gauge, -1 times 100 to give us percent. And it will have a sign using that equation. If it's negative, it'll have a minus in front of it. And if it's positive, it won't. When you're up an atom in full song, you want the turbine pressure requirement to be less than the compressor pressure gain. In this case, at 852 horsepower and at 912 horsepower, the turbine pressure requirement exceeds the compressor pressure gain. Let's look at 852. We're flowing 91 pounds per minute mass airflow into the compressor, and we're increasing the pressure across the compressor by 46.1 psi. So that's the compressor pressure gain. The turbine pressure requirement is 42 psi. Moving to 912 horsepower, we're up to 94, almost 95 pounds per minute into the compressor. So it's pumping more air. It's going to take a little more work from the turbine. Across the compressor, our pressure gain is 47.1 psi. So that's about 2.2% more pressure gain than at 852. So we picked up a pound there. But going to the turbine, we're now up to 47.4 psi turbine pressure requirement. That's a 12.9% increase in turbine pressure requirement. And the turbine pressure requirement now exceeds the compressor's output. It's upside down. That's negative. No bueno. The bottom line, the bottom axis here, running horizontally, I'm calling the X-over or crossover line. That's where the pressure would be equal compressor and turbine. At 852 horsepower, it's a pretty happy situation. The compressor efficiency is 74.5%. We're pumping 91 pounds per minute. The compressor gain is 46.1. The turbine requirement is 4.1 pounds less than that at 42. And the boost to back pressure ratio is a positive 9.8%. When we went to 912, this is where the wheels came off. The compressor efficiency is starting to drop. The shaft speed of the turbocharger in both cases here was around 109,000 RPM. But we asked the compressor to move more air, and it's telling us, yeah, I'll move more air, but I won't do it as efficiently. So it's heating the air a bit more doing it. It's dropped down to 73.1%. We're not in the weeds here. You know, until I get down in the 60s, I'm not going to have a nosebleed over this. It's up about 4 pounds per minute mass airflow, but it's still happy. The compressor pressure is 47.1. We've gained a PSI there over the previous run. But here's exactly where the wheels come off. The turbine requirement. Instead of being, as on the previous run, 4.1 PSI lower than the compressor, it's now 0.3 of a PSI higher than the compressor. That's a 5.4 pound increase in turbine requirement compared to a 1 pound increase in compressor production. And it's a boost to back pressure ratio of a negative 0.6%. That boost to back pressure ratio is 10.4% worse than it was at 852 horsepower. We need more turbo, that's what I'm saying here. So how does this impact the engine? I've got another new parameter for you here. It's the engine scavenge ratio. This is the intake plenum pressure feeding the ports in the intake manifold in PSI gauge divided by the exhaust manifold pressure at the outlet in PSI gauge. What we're looking at is port to port. In other words, what's the pressure ratio or the scavenge ratio across the engine? Everybody would probably want a positive scavenge ratio. I know I would. I'd rather have the intake port pressure be higher than the exhaust port pressure. We've done a little cylinder cutaway here with the piston at top dead center on the firing stroke. And we're comparing that intake plenum pressure to the exhaust manifold pressure. At 852 horsepower, we were 43.2 PSI gauge in the intake plenum, and we were 51.3 PSI gauge at the outlet of the exhaust manifold. That's 8.1 PSI negative. Doing it in percentage, that's 15.8% negative scavenge ratio. Moving to 912 horsepower, remember we've gained 7% in horsepower here. The intake went up to 44.4 PSIG, and the exhaust went down to 47.6 PSIG. So we got a 1.2 PSI increase at the intake port and a 3.7 PSI decrease at the exhaust port. Who says back pressure doesn't matter? That reduced the scavenge ratio from 15.8% to 6.7%. It's still negative, but that's a 9.1% improvement from 15.8% to 6.7%. This is proof that you can find horsepower by changing a tailpipe. Come on, children. Stop with this, the tailpipe doesn't matter bullshit, okay? When you go from 15.8% scavenge ratio to 6.7% scavenge ratio, what is that telling you? It's telling you there's less residual exhaust in the cylinder at valve overlap. it tells you you're going to get a higher cylinder fill percentage because there's less exhaust left in the cylinder. So the orange zone represents the exhaust gas that's still in the cylinder that would be the hell out of there if you had a positive scavenge ratio. Here's a pro tip. If you like these new readings, you only get them on an iDash. Now let's move to cause and effect. We improved the cylinder scavenge. That resulted in lower residual exhaust in the cylinders, improved cylinder fill, lower initial temperature in cylinder, and lower exhaust pumping losses. Let me give you the results. We wanted 1600 degrees EGT to be our comparative point. So at 1600 degrees, we gained 51 horsepower. 5 horsepower of that is the intake system. So we've got 46 horsepower here and all the things that center around that. But we'd set a higher limit on EGT. We took it to 1650, which was 912 horsepower. And we did that despite the injection duration now approaching 40 degrees. We did this despite the turbine going into choke, because that's what's happening. The precision turbo is a magnificent piece, but every turbocharger has its match. We've pushed the turbo beyond its match point. So I called up Dan at Precision. We talked about it. I told him what I was looking for. He's building a turbocharger. I told him, use your judgment as well as mine. We're partnered up on this. So there'll be one coming very soon. And we're going to have a variety of turbine housings to be able to tune the shaft speed versus mass flow, AR ratio changes. So we made 912 horsepower, and our fuel used per horsepower dropped 2.8%. You heard me right. We made 60 more horsepower with a 2.8% fuel economy bonus. Once again, guys, that back pressure matters no matter where the hell you reduce it at. How do we measure that? We measure brake-specific fuel consumption. We've got a fuel flow meter and we know the horsepower. How many pounds of fuel does it take to make 1 horsepower for 1 hour? We dropped from 0.428 pounds to 0.416 pounds per hour. That's a 2.8% increase in fuel economy, making 60 more horsepower. So what's up next? Well, the Denso high pressure pump has taken us to 912 horsepower. Everybody would have bet against that happening, but it happened. But we noticed on the 912 run, even with 90 pounds of lift pump pressure into that Denso pump, we were losing rail pressure. Not a lot, maybe 40 bar or so over the 852 run. We were able to pull it off, but that's part of the reason that I've got that wider crank angle injection duration. So it's time for some magic from S&S. Andrew sent out a set of 100% over injectors to replace the 50% over injectors. That'll help with crank angle as well. And he sent out one of his magic Cummins style CP3s. So we're replacing the Denso pump with a Bosch pump. And even better, it's an S&S Diesel Motorsport 12 millimeter stroker. The guys jumped right on the engine when we stopped. They've got the injectors in, they've got the stroker pump on. Third item we're doing is we're installing a comp cam. And Mike, you getting that thing in there? Yeah, he is. We're good. So the comp cam has got my fire lit, let me tell you. Also, we're going to change the oil filter in an effort to get less pressure drop than we get with the current oil filter. The pump and injectors will give us the fuel. The cam will process more air per cylinder cycle, and the bigger precision turbo will provide us greater mass flow and less back pressure, which should help the scavenging. And if I'm lucky, we're going to blow this pup past 1,000 horsepower. Stay tuned.